Alrighty, here we are back for the final part of lesson 8 about aerodynamics. In this one, we're going to talk about thrust and drag a bit. So let's get to the notes here. Let's start with thrust. First thing is thrust is the forward acting force that opposes drag. During straight and level unaccelerated flight, the forces of drag and thrust are equal. We talked about that at the very beginning of this lesson. Thrust is usually provided by the engine. When you increase thrust over drag, it causes the aircraft to accelerate. When you reduce thrust, drag causes the aircraft to decelerate. And we're going to talk a lot about that in class. So let's talk about drag. 3 kinds of drag. Number 1, parasite drag. This is caused by all the stuff hanging off the airplane. It's basically hitting those air molecules, creating resistance, and causing the aircraft to drag. Antennas that are 90 degrees angle of the wing to the body, rivet screws, all of these are examples of parasite drag. The second kind of drag is induced drag, and this is generated by the airflow of circulation around the wing as it generates lift. Induced drag is a byproduct of lift. Anytime you're producing lift, you're producing drag, and we're going to talk about wingtip vortices in class. Then we have total drag. This is the sum of the induced and parasite drag together. So here we have our total drag if we plotted it on a curve. And then we have induced and parasite. And down here is speed. So you can see as the speed increases, parasite drag increases because more air is hitting those things on the plane. As speed increases, we don't have to pitch up as much, so we're not having to produce as much lift. Therefore, induced drag goes down with speed. So airspeed slowing and speeding up has different kinds of drag doing different things. Notice there's a low point on total drag right here at the speed of 80 knots. That's our best climb speed. All right, let's talk about ground effect a little bit. This is when lift is created and you get a downwash of wingtip vortices. This causes drag on the surface creating it. If we could stop those vortices from forming, we could reduce drag. So when you're near ground in flight, the ground disrupts the creation of these vortices and you can fly at a slower airspeed without stalling. That's called ground effect. So we're going to talk about that in class a bit. Flaps. Different kinds of flaps. So what's the purpose of flaps? Well, basically what flaps do, they allow you to steepen your approach angle without increasing airspeed. You can produce more lift, giving you a lower takeoff and landing speeds, and you can reduce the length of your takeoff and landing roll. Let's talk about axis of rotation. This is a part of aerodynamics that gets kind of brushed over in flight training a lot, but a lot of what we talk about happens around these 3 axes of rotation. There's the vertical axis, the longitudinal axis, and the lateral axis. And when we talk about stability, stability is the inherent ability of an airplane to return or not return to its original flight condition after being disturbed by an outside force, such as rough air. For aircraft, there are 2 different types of stability, static and dynamic. I'm just going to say this. Get this down in your notes. We're going to talk about this in class. This is one of those things that took me a long time to really understand until I had a good flight instructor explain it to me. So I'm going to try to explain it to you in class. Let's just fill out the notes for this one, and we'll definitely we'll get to the real explanation of this in class, because just trying to read this in a book or even watch somebody explain it on a video, man, it is tough to understand. So most aircraft are built with stability in mind, but that's not always the case. Some aircraft, like training airplanes, are built to be very stable, but others, like fighter jets, they tend to be unstable, and we're going to talk about that in class. So the 2 types we're going to focus on are positive static and positive dynamic stability. So let's start with static stability. It's the initial tendency of an aircraft to return to its original position. There are 3 kinds of static: positive, neutral, and negative. So let's say you're flying an aircraft and you hit some turbulence and the nose pitches up, and immediately after that happens, the nose lowers and returns to its original attitude. That's an example of positive static stability, and it's something you see flying an airplane like a 172. Then dynamic stability is how an airplane responds over a period of time to a disturbance. And it's probably no surprise that there are 3 kinds of that as well: positive, neutral, and negative. So if you're trimmed for level flight and you pull back on the yoke and let it go, it'll immediately start pitching down. That's that positive dynamic stability. And over time, the pitching, it'll kind of oscillate. So kind of do this. You disturb it, and it kind of goes down. It'll actually pitch down initially, and then it'll just kind of ride this wave till eventually it's just back to straight and level flight again. We'll talk about that in class. Something we need to always understand in every flight is center of gravity. In fact, we calculate the center of gravity before every single flight. So there's the center of gravity is where all three of those axes we talked about earlier, vertical, longitudinal, and lateral axis, all intersect at the center of gravity. And all the rotation is around those different axes of flight. It's basically measured from a place called a datum. So they pick some place on an airplane, and then they said that's the datum point, and they measure backwards, usually in inches. They say 76 inches CG aft of datum, or 9 inches the CG is positive of datum. And I'll give you some examples of that in class as well. So there are different effects. You could have a forward CG and an aft CG. Now, if you're in limits, there's a limit for the CG. If you're outside of limits, you can have really bad effects. But if you're inside, you can expect some things like for the forward CG, if it's inside limits but forward of center, increased stability, lower cruise speed, higher stall speed. If you tend to have a CG aft, you will have less stability. You can have a higher cruise speed, and I'll explain that. It has to do with the angle of attack of the wing. A lower stall speed, but it is hard to recover from a stall. Remember when you have that aft CG, and that's pulling the tail down because it's aft. Aft, it means back. If it's aft CG, you're trying to push that nose down and break that stall, but if there's too much weight back here, you may not have enough elevator to overcome that. And we'll talk about that. It has to do with the length of the arm or the lever from CG to that control surface. We'll do some problems in there. All right, let's talk about load factor and turns. The forces of a turn can be divided into vertical and horizontal components of lift. When you're straight and level, all the lift's vertical. It's all pushing up on the airplane. When you turn, though, we trade a little bit of that vertical lift for some horizontal lift. So vertical lift, horizontal lift. When we turn, we lose vertical lift and we get a little bit more horizontal lift. That's why when you're flying the simulator and you turn, the nose drops. You got to pull back. You've lost vertical lift. Load factor is where you basically take so load is the force that must be maintained by the aircraft structure. Load factor is measured in G's, and 1 G equals 1 time the force of gravity. So as you turn, you actually increase the G's of the plane, meaning the plane's heavier. It's not really heavier, but the forces on the wings are much higher than it is in straight level flight. So when we turn, we put more load factor on a plane. How much? Well, a 60-degree bank will result in 2 Gs. So if your aircraft weighs 2,000 pounds, but you put it in a 60-degree bank, it's exerting 4,000 pounds of force on those wings. So let's talk about left turning tendencies. So left turning tendencies in an airplane. We have torque, P factor, gyroscopic precession, and spiraling slipstream. I'm going to go into all these in detail in class. Just get these written down in your notes. First one's torque. So you throttle up that engine. It wants to go down the runway. That crankshaft spinning that prop around. Well, it's trying to push the aircraft in. It's trying to push it to the left. So it's trying to pull it opposite of that crankshaft rotation. So you have to add right rudder. When you're at high power settings, but low air speeds. Because when you have a higher airspeed, you have forces acting on the plane trying to keep it straight. But low air speeds, the wings and tail aren't doing anything. So you're having to overcome that. And the torque of that engine is trying to pull it to the left. Try to pull it to the left. The next one is a P factor. And that's as the downward sweeping blade is much higher angle of attack than the upward slipping blade. So basically one side of the propeller spinning has more thrust than the opposite side due to the angle of attack as it's taking that downward bite of air. Gyroscopic precession, you don't see that as much. You see that mostly in tailwheel airplanes, but basically the plane wants to when it raises up, it wants to pull to the left once again. I'll explain that in class a little more with a model. Spiraling slipstream, that's basically when, as the air wraps around the fuselage, it strikes the tail on the right side, which causes the airplane to then go to the left once again. So, right rudder, what's the end effect of all this? When you're taking off or you're flying at low speeds like you're climbing out, you're going to need some right rudder to try to keep that nose straight as you move ahead. Make sure you write down your questions in your notes. I'm going to ask about questions in class. That's the best time to ask them. So write them down as you're learning this stuff, and let's answer those questions when we get to class. Thanks.